Hello and welcome to Bay College's online intermediate algebra lectures. I'm Jim Helmer. Today we're going to look at section 5.1. Section 5.1 is actually going to be split into two separate videos. This one we're going to look at rational numbers, rational expressions, how we deal with rational expressions and simplifying them, and when we look at domain. So the first thing we're going to recall is what is a rational number. A rational number is any number that can be represented as a whole number divided by some other whole number. Maybe it's 1/2 or 1/7 or maybe even 3/1. A whole number such as 3 can be represented as a rational number, 3/1. Rational expressions are any expression that can be represented as polynomials. A polynomial over a quotient polynomial, and that becomes our rational expression. So if we look at a few of these examples, this is an example of a rational expression where we have this polynomial of second degree over this polynomial of second degree. Same thing here. We have 2x squared plus 5x minus 12 is our numerator polynomial, and our quotient polynomial is 2x minus 3. Here in the denominator, here x minus 1, and here x squared plus 6x minus 7. Now, when dealing with these rational expressions, this is where you're actually going to see all that hard work you did with learning how to factor actually applying. We're going to find a place for it, we're going to work with it, and we're going to factor, factor, factor. It is the most crucial concept when dealing with rational expressions. Because a lot of the time, especially when we're dealing with functions that contain rational expressions, is we have to determine domain. So just for practice sake, we're going to look at these as examples. Let's just pretend they're functions. We'll also look at other ones. And we're going to look at the domain. We're going to find the domain. And we do that by simply factoring. Let me grab a piece of chalk here. Now, to find the domain, we want to factor. We want to factor just the denominator, because what we're looking for is what values make us divide by 0. We have a polynomial in a denominator, and we know we can never divide by 0, so that's what we're going to look for. We're going to say, OK, what does this factor to? Well, maybe you recognize this as a perfect square trinomial, and you can jump right to it. Or maybe you say, all right, what are the factors of 4 that sum to -4? Maybe you see it's -2 and -2. Well, either way, what method you use to factor it, you should come to this conclusion. We just factored this. X minus 2, this quantity squared, is this. Now we can use the zero value theorem. And maybe you remember that term, or maybe you don't, but I hope all of us remember anything times 0 is 0. If this was equal to 0, which we can't have, so we say we don't want it to equal 0, what value of x would make this equal to 0? Well, if x is 2, because 2 minus 2 is 0. 0 squared is still 0. So what we want to do is we want to exclude that value, because that makes our denominator 0. So for domain, you can write it as x not equal to 0, or proper notation, x such that x is not equal to 0. Or you can use set notation, or excuse me, interval notation. This is set notation. We'd have from -infinity. Oh, I'm sorry. This should be +2, because 2 minus 2 is 0, right? So we don't want to have the value 2, because we don't want that to be 0. I do apologize. All right, so we have -infinity up to the value of 2, but we cannot include it, so we use our parenthesis here. And we want to make it a union parenthesis from 2 to infinity. And what this says is we can use any value except 2. I like set notation in this example. It's a little easier to write x not equal to 2. And let's clean that up so it's nice and legible. X not equal to 2. All right, let's look at the next example here. In our denominator, our quotient polynomial is 2x minus 3. Well, that's already factored. I can't factor it any further. So we're just going to leave it as is. And we're going to say our domain is x such that x, if I were to set this to equal to 0, I'd add 3 to both sides and divide by 2, which is going to say 3/2. This is the value I must exclude from my domain. x cannot equal 3/2. Moving on to this one. Now we'll see we have x squared plus 6x minus 7. And we can factor this as well. So if we look at this, what are the factors of -7 that combine to give me 6? Well, the factors of -7, well, that's just 1 and 7. To give me a positive 6, well, the larger number would have to be positive. So if I factor this, the factors of 7 are 7 and 1. This is negative, which means one must be positive and one must be negative. Which one's which? Well, this tells me the larger value. So we get x plus 7, x minus 7, because if we look at our outer and inner terms, if we were to FOIL this out, 7x and -1x is 6x's when we combine those like terms. So now we can use the zero value theorem. If this was equal to 0, these are the values I must exclude. X cannot equal, for this factor, -7, and for this factor, +1, because 1 minus 1 is 0. So these are the values we'd have to exclude. Now, if we were writing this in interval notation, this kind of helps me show why I prefer set notation when looking at domain over interval, is because I would actually have to write this into 3 separate intervals and have 2 different union symbols in there. And that can get kind of long and tedious. So for my students, I just ask that you write this in set notation, unless asked otherwise. All right. Now, the thing about rational expressions, well, they apply when we turn them to rational functions. This is a function. This is actually a linear equation, but it's represented as a rational expression because we have something in the denominator here. Now, if we're looking at domain, is there an x in the denominator? In this case, there is not. So there is no value of x that will ever change this 4 to a 0. Okay, so there's no value of x that we need to exclude. Well, what does that make my domain? It makes my domain all real numbers. There is no value of x that makes me divide by 0 in this case, because the only thing in my denominator is a 4. So I can say x such that x is all real numbers. I could write it in interval notation, -infinity to infinity. Or I can use this symbol, which means all real numbers. I can say x is all real numbers. There's nothing we need to exclude. Now, moving on to the next example. Well, now we can see there is an x in the denominator. So we have to say, what are the values of x I can't put into this function? What is the domain of the function? And hopefully we recall finding domain in previous algebra classes. Now, if I look at this, I say, OK, well, this is just a linear factor here. It's as factored as I can take it, so I don't have to factor anything. So let's just set it equal to 0. What value of x would make it 0? That's the value of my domain. And I just abbreviate domain semicolon here. X cannot equal 2. Because 2 minus 2 would be 0, and I cannot divide by 0. So we have to exclude that value. And we find the domain. Now, the next example, we have x squared plus 16 over x squared minus 16. This is our function h of x. Now, we don't really have to concern ourselves with the top. And please, I implore you, many students would say, oh, well, if I'm going to reduce this, the x's squared cancel 16. That is not the case. When we have sum or addition, those rules of exponents do not apply to sum and differences. Okay? So we have to factor this. We have to. And if hopefully we recognize this is one of our special factors, it is the difference of squares. Hopefully we recognize 16 as a perfect square. And difference of squares, well, that middle term of our ax squared plus bx plus c must have canceled out. So that tells me right away that these have to have different signs. That middle term needs to cancel. We know the first term is x times x, and the last term is the difference of these squares, different signs of the square. Well, 4 is the square root of 16. 4 times 4 is 16, so we can always check our work. If we FOIL it back out, x times x is x squared. 4x and -4x goes away. No middle term here. And 4 times -4 is -16. So now we can say, what if this were equal to 0? We cannot divide by 0, so we have to exclude the values -4 and +4, because those are the two values that would make either of these factors 0. And we know that 0 times anything is 0. So if we find one, doesn't worry about the other one. Find the next factor, don't worry about that one. Because if one of them's 0, they're all 0. 0 times anything is 0. So now let's look at some examples of what we might see where we have to simplify some rational expressions. Now here, essentially what we have here is we only have multiplication in the numerator and in the denominator. And then we have this division, because that's what a fraction is. It says divide these two values. So the only operations we have here are multiplication and division. In this case, we're just canceling common factors. One thing to keep in mind, I kind of briefly touched on it, you cannot cancel terms. You can only cancel factors. And we'll see, I'll stress that again in this example. But here, we just want to work it left to right. If we look at 12 and 48, these are just numbers. And like any fraction, always reduce your fraction. So let's deal with these numbers, 12 over 48. Well, that reduces because both are divisible by 12. So I can reduce it to 1 over 4. And we don't need a 1 because we're going to have some variables up there. So we deal with the number. Now we can just move left to right. Well, I have a's on top and a's on the bottom. And we recall any number divided by itself is 1. And that's why we can cancel factors. 4a's on top can cancel 1a on the bottom, leaving 3a's on top. Or maybe you remember your rules of exponents. Hopefully you do. We can use the quotient rule. 4 minus the exponent 1 is 3, a to the third. A to the third, well, a positive exponent says we're going to leave it up there in the numerator, a to the third power. Now we have our b's. Well, if you cancel it, well, 5b's on top will cancel 5b's on the bottom. That would leave me 2b's on the bottom. So maybe we just say that, or maybe we use the quotient rule of exponents. 5 minus 7, the top minus the bottom, would be -2. That negative, using the reciprocal, tells me it goes into the denominator. So hopefully, we still recall our rules of exponents, because they still apply, just like factoring applies, to these rational expressions. And now we have our c terms. 1 on top can cancel 1 on the bottom. And this is the simplified form of this. So we want it in simplest form. We're essentially just reducing a fraction. All right, so a cubed divided by 4b squared c is our simplified expression. Now let's look at this one. It breaks my heart to see students cancel b's and cancel a's in this example. Because of this addition or subtraction, these signs say our rules of exponents no longer apply. There are no exponents that talk about sums and differences. So what we have to do is use our tool of factoring. What can I factor out of the top? What can I factor out of the bottom? Because I want to reduce common factors. So here I look at this and say, hey, they both have a -8. Let's factor out a -8. That would leave me with a and a positive b. Right? We factored out that negative, and we factored out that number 8. In the denominator, well, I can't factor anything there. I have a plus b. Now, if we assess our factors, I have -8 times the quantity a plus b. This a plus b is a factor. Divided by a plus b, this entire quantity is a factor. So I can cancel common factors. And the only thing left is -8. And we don't want to think of this as just canceling. It's reducing to 1. Anything divided by itself is 1. 1 times -8 is -8. So make sure you don't just think of it as going away, because there is essentially a 1 there, especially if it canceled the other way around. If that 8 was in the denominator, it would have to remain in the denominator. A 1 would be on top. All right, let's look at this example here. Well, this one we have to do a lot of factoring. I cannot just start canceling because of these sums and differences that are in here. I must factor because I want to cancel common factors. So I look at this and I say, OK, well, let's use those tools. What are the factors of -72 that have a difference of 1? Well, I know 8 times 9 is 72, and 8 and 9 have a difference of 1. Well, the larger value must be negative. So I'm going to factor this, and I'm just going to write its factors above it for space sakes here. X minus 9, x plus 8. Negative 9 times 8 is negative 72. Negative 9x's and positive 8x's is negative 1x. And of course, x times x is still x squared. So that is factored correctly. I kind of multiplied it out to check my work. And I'm going to do the same thing on the bottom. Maybe I say, what are the factors of 81 that combine to give me negative 18? Or maybe I recognize this is one of our special products. This is a perfect square trinomial, where 81 is a perfect square of 9, and negative 18 is twice that factor of 9, but it would be negative. So I can go ahead and write x minus 9 squared. And that's what it would factor to no matter what method I use to factor it, x minus 9 squared. And now we're ready to reduce. We have everything in a factored form. And I could say, hey, I have a factor of x minus 9 up here and 2 factors of x minus 9 down here. Just like we canceled the common factors up here, 4 on top could cancel 1 on the bottom, so on and so forth. I can say one of these x minus 9s can cancel one of those x minus 9s, top and bottom. It reduces to 1. So what's left? Well, I have, oh, excuse me, we don't even need parentheses now since it's a single linear factor, and x minus 9 on the bottom. So this ugly looking thing with all these additions and subtractions and larger numbers in there, once we factor it and reduce, we see, well, it's just x plus 8 over x minus 9, a relatively simple rational expression. All right, we're going to move on to the next example here. And sometimes they're not going to be in the form that we want them. If we look at this one, it's 4 minus x squared. And we're so used to seeing our polynomials in descending order. But the reason why it's written this way is because the positive values first and the negative values second. So what can I do to change this? How can I have this x squared first? Well, I could just switch them around and maybe have it as negative x squared plus 4, because this sign belongs to that. Its coefficient is negative 1. This one is just a positive 4. Now, looking at that, we're going to see, hey, that negative out there, there's something I can do with that. But let's go ahead and factor this first. If we factor this one up here, we'll say, hey, maybe I recognize it as a perfect square trinomial, x plus 2 quantity squared. So I just write it above it. OK, so I've dealt with that. It's factored now. Now here, can I factor this? Well, maybe it's not in the form I'm used to because the signs aren't right. Well, we can always change the signs. And that's by factoring out a negative 1. So I'm going to factor out this negative 1. And that just changes the sign. X squared minus 4. So this becomes a positive. This becomes a negative by factoring out that negative 1. Now, for board's sakes here, because we're a little crowded, I'm just going to rewrite it. It factored to x plus 2 quantity squared over negative 1 times x squared minus 4. One thing we should always check, once we've factored, ask ourselves, can we factor further? Well, we have the difference of 2 squared quantities. I recognize 4 as a perfect square. So it does factor further. That negative 1 comes along for the ride. It's x plus 2, x minus 2. The difference of squares always factors to that square root value of 4, plus or minus. We change the signs, the different signs from the difference of squares. And now we can see, hey, I have 2x squared plus 2's on top and 1 on the bottom. So 1 on top can reduce the 1 on the bottom to 1. Now what's left? X plus 2 over negative 1 times x minus 2. Now, for some, this is fine. You could leave it like this. But for others, we don't like to see negatives in the denominator. And traditionally, that actually comes from the English language. You might say negative 1 half, if you had negative 1 half. Or you might say negative 1 half. Well, either way, you use the same terms to describe that. But no one in proper English would say 1 negative half. That negative does not belong in the denominator. It doesn't sound right. So what can we do with it? Well, since these are just factors, it's a negative 1. Whether I multiply by a negative 1 or I divide by a negative 1, I get the same result. Because 1 doesn't change the value, negative 1 only changes the sign. So I can finish and maybe put that negative out front, or I can distribute it through the top. And I'm going to prefer to distribute it through the top. It just changes these values to negative. Do not cancel common terms, only common factors. So some students might want to take it a little bit further and say, oh, this value is this. It's not. We stop right here. All right. And again, when we look at negatives, sometimes they can throw us off. We all make sign errors, even your instructors. So what we want to do with this is just assess it first. We say all of our terms are positive. And if we know about the commutative and associative property of addition, if it's all addition, the order doesn't really matter. 2 plus 3 is the same as 3 plus 2. So we can actually change the order. And I want to put this in descending order. So the top, I'm not going to change at all. The bottom, I'm going to just change the order, because x plus 19 is the same as 19 plus x. And now I can see, hey, x plus 19 is divided by itself, x plus 19. So sometimes changing the order, whether it be putting it in descending order or maybe having to change the sign or switching it around, as long as you don't break any rules of math, we can see in this example, this does reduce to 1. We cannot say, oh, it just cancels. There's nothing left. There is something left. Any number divided by itself is 1. So if we think of this as canceling, we have to remember that it is still 1. Now, we're going to look at one more example. It's probably the most complex of the examples that we're going to take a look at today. And we can see here we have 4 terms. The most we've seen over there maybe had 3 terms. This one has 4 terms. And maybe you look at it and say, well, hey, maybe we can combine like terms. Well, it's put this way for a reason. And it's to help you review one of your rules of factoring. And that is factoring by grouping. Whenever you see a 4-term polynomial, it's best to maybe try to factor by grouping. So what we're going to do here is we're going to just factor by grouping the top for review, and we'll factor by grouping the bottom as well. So I'm going to look at the first 2 terms of this 4-term polynomial and say, what do they have in common? Well, they each contain an x. So if I factor out an x, that's going to leave me with x minus 2. Factor that x out. If I multiply it back through, I get back to this. So I'm checking my work as I go. These 2 factors have a 4 in common. So I'm going to factor out a positive 4. And if I do that, it leaves me with x minus 2. Well, this is really good news at this point. If I look at x minus 2 and x minus 2, now that I factored it into 2 terms, I can say, hey, they have a common factor. And I can pull that out. And I'm going to write it right over here. X minus 2 is common to the values x and 4. So now I factored that using the method of factor by grouping. And I'm going to do the same thing here. Now, if these terms were combined, I might have to use another method, the AC method, which is also part of that is factor by grouping. So if I combine these like terms, sometimes I'd be working in circles there. So we're going to leave it like this, and we're going to do the same thing we did on top. What do these 2 terms have in common? Well, they each have an x, which would leave me with 2x plus 3. And now what do these 2 terms have in common? Well, I see 8 and 12 are both divisible by 4. I'm going to factor out a positive 4, and that leaves me with 2x plus 3. And we say, hey, 2x plus 3 is common to both of these terms, so I can factor it out. 2x plus 3 are both multiplied by x and 4. And now we've done all that factoring. It's time to reduce. So what I'm going to do here is I'm just going to say, hey, a common factor top and bottom. X plus 4 divided by x plus 4 is 1. And 1 times this quantity doesn't change it. Let's just take it one more step further. What if this starting value here was a function? I'd have to find its domain. Well, the domain actually starts back here. Once we have it factored, we exclude all the values that make it undefined, even if one of them cancels. So keep that in mind. You might see a question like that. You know, what's the domain of this function? If this was represented as a function, you'd find both of these and then write it in simplest form. So if we were finding domain, let's go ahead and do that right here. -3/2 is the value that would make this equal to 0. It's always the opposite of this, divided by that coefficient. Or we could set it equal to 0. We'd end up subtracting 3 and dividing by 4. So x cannot equal negative 3 halves. And for this factor here, the x plus 4, x cannot equal negative 4 because that makes this factor 0. And we can never divide by 0. This concludes part 1 of section 5.5 notes, simplifying rational expressions. Thank you.